in-star seminar. Today we're going to be hearing from Scott Peckham. I'll do a brief introduction and then let him take it away. So Scott's been at CU Boulder for a number of years now, and his interests are rooted in physics-based, let me read this, physics-based mathematical and numerical modeling of Earth surface processes with a focus on hydrology and landscape evolution. So he's interested in fluid dynamics, scaling laws, river networks, population dynamics, etc. And much of his work has been focused on developing cyber infrastructure to support geoscientists. And I think we're going to be hearing about a few of those different projects today. And he's authored numerous open source models, including spatially distributed hydrological model called TopoFlow, and a fluvial landscape evolution model called Erode. So give it up for Scott and let him take it away.
Thank you. Well, thank you everyone for coming. Can you hear me? Or I guess this is just for the Zoom, right? Okay. So this is going to be a story of some work I've been doing consulting with NOAA for about the last 4 years now. And it's going to, since the other two people that were supposed to talk during the new seminar canceled, I got the whole time. So you're stuck with me for a while, but I'm hopefully it'll be fun. And I've got several sections. So this is really broken into about 5 little mini talks about different things I worked on in this process. But if you've worked with NOAA, you know they like to talk about research to operations a lot. And they work with, they're the ones behind all these CIs that are out there, these cooperative institutes. So Ceres is one of their CIs. The newest one is Cairo, which is focused on hydrology. And the RO stands for research to operations. And there's about 10, I guess, altogether. But they've had this big partnership with academia for a long time to try to drive their development to make things better. So the talk outline is going to be, well, the first part is that little block at the top. The two key words here are heterogeneous things like models and data sets and trying to make them interoperable. And so if you're familiar with the FAIR acronym, we're focused on the I. We're trying to make things interoperable. And, you know, it's not just the models we have in the US, but we have all our agencies, we have all our universities, but then every other country has their agencies and their universities. So there's a lot of reproducing things or like reinventing the wheel, a lot of data sets, a lot of great models spread across the whole planet, but they're in different languages and they're not necessarily interoperable. So I'll talk about the next generation water resources modeling framework first, then a little bit about BMI, which many of you have probably heard of, then the scientific variables ontology, the TopoFlow model, and finally wrap it up with Harbor. So this is just kind of a transition slide, but it's got a URL on it. So if anybody gets this talk, they can follow these links. And there's also paper references. So this is a paper about to come out by Ogden and a bunch of us talking about the work on NextGen. Now, many of you have probably seen this plot or something like it that people show when they give talks on NextGen or National Water Model. And this, a few years ago, starting about 2016, and I'll show a timeline here in a second, they decided to build this model that would not just model like 3,600 places, but it would model 2.7 million stream reaches across the whole US. And so they would look at the water depth and the flow and all that for all these, but they do it operationally. So they produce products. The short range products are predicting, they run hourly and predict 18 hours ahead. The medium range ones are running every 6 hours and look 10 days ahead. But sometimes you'll see people playing an animation of this where the colors change as the flow gets more or less throughout that plot. Now this is sort of a timeline, which I think is good to see, to kind of get a perspective of where all this fits together. So the first version of the National Water Model, version 1, which was built on Wharf Hydro with my friend Dave Gotchis as one of the people involved in that, was 2016. And then it was going for a while, and there was some community feedback that says, well, some of these things are not so good. We can't make it do well everywhere. It's just one model trying to rule them all for the whole US, and it's just not doing well everywhere. So there was an audit by a group called, from the General Service Administration called 18F Group, and they were asked to audit the code base, and they recommended some major changes. And around that time also 2.0 was released, which is not related to the changes, but they were trying to see if they could work with what they had to make it come closer to what was recommended. Now that 18F group, by the way, was killed by Doge. So his whole job is to make software more efficient and better. And so it's interesting that the Department of Government Efficiency shut down the efficiency side of things. But anyway, so then in 2020, in August, this group met a bunch of U.S. water prediction agencies. And so it's pretty good showing with NOAA, U.S. Army Corps of Engineers, Bureau of Reclamation, USGS, DOE was there. And they said, we got to do something different. We got to make something that's better than the National Water Model, that's more plug and playable, that's more modern architecture. And so they met again a little bit later to talk about requirements. And then, unbeknownst to me, they, without my involvement, they looked at a bunch of model coupling interfaces and they chose BMI. And they also chose another standard called high features, which is part of the OGC Water ML standard. And that was going to be their two community-based standards that we're going to build this new platform on top of. And they looked at lots of options like ESMF and other options, but they chose BMI as what they're going to go with for that. Then right after they made that decision, they asked me to join their development team. So I started consulting with them. And for about 3 years, we worked on lots of things related to that. And we gave talks at AGU and AMS meetings. And NOAA was hosting these meetings, the sessions at these meetings for a long time. But then the new administration kind of killed travel. So there's no such session this year at AGU, and I'm not going this year. This was work with Linker as one of the contractors. Linker is a company they work with to find people to work with them. And then in 2023, NOAA decided to give a big pot of money to Raytheon to build the operational version. And that turned out to be a pretty bad decision because they've been way behind on all the deliverables, and it's been not a happy story. But they're supposed to have that all finished by 2026, which doesn't look like it's going to happen. So there's kind of a fork that happened where there's an academic version of next gen, which I'll talk about more, that's become easier to use. And then there's this operational version that Raytheon's supposed to build for us, but they're really not doing very well. Now, Cairo in 2025, that's one of those cooperative institutes that just formed. They created NextGen in a box, which is a containerized version of NextGen that makes it a lot easier to use, like a way easier to use. And I'll talk a little bit about that too. But that's kind of the history of this effort. Now, BMI was something we developed when I was the chief software architect for CSDMS. We wrote a paper in 2013 on this, and it has really taken off. After it was chosen by this group of multi-agency group, everybody started converting their models to have a BMI interface. And this is just a list of some of them. And you'll surely see something you recognize in here if you do hydrology modeling, because there's Wharf Hydro in there and ModFlow and SUMA by Martin Clark. And so if you know hydrology names, you'll recognize a lot of these authors' names, but you might recognize the models too. And there's also coastal models in here like Schism, GeoClaw, Delft 3D, DFlow, Flexible Mesh. And so this has really started to take off. It started to snowball. And the next slide shows a few more because they didn't all fit on that slide. But some of these I didn't even know about till I was Googling for this talk, but some of the linkages that happen through BMI that people have written papers on are Wharf Hydro to ModFlow, GeoClaw to CFE, CWAT-M to ModFlow, Metaswap to ModFlow, and these two from University or Iowa. Is it University of Iowa or I don't know, but it's Abraham Demir, if you know who that is, and his team have shown how to do this with JavaScript. So they have a BMI for JavaScript that they're using a couple models over the web. And so as I was working with NOAA, I helped do the BMI implementations for their machine learning model called LSTM, and this other one, which is CFE, which I'll talk more about. CFE, by the way, which was on this slide, is spelled out as the conceptual functional equivalent model. And Fred Ogden, as the new chief scientist for NOAA, thought that we could basically capture the essence of the National Water Model with something that was functionally equivalent, but a lot simpler. And so he's been developing that, and it's proving to be just about as good as what the National Water Model was able to do. Now, I mentioned the hydrofabric and this high features standard. So this is a standard for thinking about how river basins are put together and what the terms are. So it's concepts like catchments with their boundaries and a nexus, which are places where things come together, and flow paths. And so they've built this, it really is like a fabric, which can be scaled in and out for different modeling exercises in a very consistent way for the whole US. And both USGS and NOAA are now using this hydrofabric for their water modeling efforts. So this underpins the national water model and what especially the next gen framework is coming up. So this next part is going to be a little bit about BMI. These are a couple papers. This is the first paper that we wrote with Harry Cutton and Bojana Norris and me. And then the second one was I was working with a team on an Earth Cube funded thing, and a postdoc named Peishi Jiang was able to help us turn this into a web service thing. So all these components were now running on different servers, and they were coupled across the web and exchanging their information as netcdf files instead of through memory. And that also worked. And that's been part of the inspiration for the work that Iowa team is doing for their cloud-based stuff. Now, give you a little history about BMI. First thing is to ask, well, how can two models differ? Why is it hard to couple two models? And they can be in different programming languages. They often are. They can have different computational grids. It should be triangles, rectangles, Voronoi, just about anything, tins. They can have different time stepping schemes, which may be fixed or adaptive. They can have different variable names, which they always do. So inside, they have an internal vocabulary with their own names. Then they have their own units. And so if you're trying to connect them, you've got to reconcile these differences. You have to convert units. You might have to convert the grid. You might have to do something to temporally interpolate and so forth. So we found solutions to these things when we were working on this, and we used something called Babel with language bindings. The ESMF had a great regritter we used. We wrote our own interpolation tool for time. The standard names is something that we looked into the CF convention standard names and found problems with it. So we ramped off of that and to build something new that we think is a lot better. And then UD units from Unidata provides unit conversion tools that we used. Now, this describes the big concept, and I don't know if it'll fully sink in when you first see it, but there's in software design, there's a lot of patterns that people use, and people talk about the adapter pattern. If you look at a book on design patterns, adapter pattern is one pattern, a mediator pattern is a pattern. But this one is really an adapter mediator framework pattern. It has three main parts. It has a framework, which is a piece of software that actually does the calling to the functions through their BMI. Then it has some mediators that deal with the differences between models. So when it needs to regrid, it asks model one, what grid are you on? And this other model two wants to use the variables. So it says, okay, describe your grid to me and describe your grid to me. And I'll send that information to the regritter. It'll regrid the information that you want, and I'll convert the units and interpolate in time, and I'll send it over to you. So these models are not being changed internally at all. They're just putting this extra BMI wrapper, which is what this is supposed to indicate here. And there's also a concept which helps make this non-invasive, which is called the Hollywood principle in software design. Don't call us, we'll call you. So what, if you think about, if you wrote a model and now you have to call some outside things, your model's not your own model anymore. Now you rely on those things before you can still run, right? So what this does is it makes it so that information is provided to, you give the agent your phone number and all your information, but you just hope they're going to call you. And so that's what they do. They make all the information about themselves available. And so these are all different grids in this example. This one's a data set, which is a lot like a model with no inputs. And so they all provide information to the framework. The framework looks at who wants to talk to who. Like it matches up variables by saying, okay, you have that variable, you want that variable, but your grids are different, your time stepping is different, your variable names are different. So we're going to fix all that and automatically connect you to. So that's what this system does. And it works great. And it gives you all kinds of other options. Like you can start to build other things like a model state serializer. So once you have the BMI interface exposed for all your models, you can get what you need to serialize them. You can get what you need to write their output to some new format. You can get their output for any other purpose. You might make movies, whatever you want to do. You can keep adding tools in the framework that add more and more capability to those models. So this is something where the added value comes to the modelers, because now they can do all this great stuff with their models that they didn't have to write themselves. And they don't have to worry at all about other people's models. All they do with BMI is describe their own model. They make their own model callable, and they describe it fully, the grid, the variables, everything, so the framework can ask them about it. So that's the way this works. And the framework can be, oops, I just hit the wrong button. The framework can be CSDMS originally, or next gen, or I wrote one called Emily, a lightweight one. Now, this is a slide I had to bring back because I used this a lot in the early days of BMI. We were trying to think, Eric Hutton and I were trying to think, how can we communicate this idea of a standardized interface, like an API, to our geoscientist colleagues? And so this picture came to mind, and it's kind of a fun analogy because this is a happy bunch of very individual, heterogeneous models out here on the left, and a lot of enthusiasm and a lot of great stuff going on there. But they don't necessarily work together as a group very well. They're too different from each other. Whereas if you put a wrapper on them, which is the uniform, and you line them all up and you make them respond to the same set of commands, and that's where the analogy is really great because if you think about a soldier movie, you say halt, you say march, you say about face, permission to speak freely. They have standard things that they say, and they all understand that. No matter where they came from, they all learn to say those same words. Well, the models all learn the same thing too. They learn that initialize means get ready to go, and update means take a time step forward or march, and finalize means wrap it up. So they learn, the models all respond to the same sets of commands, just like these soldiers do, which is what makes it a lot easier to control them and make them do stuff as a team. Now, this is another way to think about BMI, look at BMI, is that the remote control on the left is supposed to represent like a universal remote control. So imagine your living room and you've got all these different electronic devices and you got a whole table full of remotes, but you like to control them all with one remote so they all understand the same commands. And so you might get a universal remote because they have such things. And that's what this does, is by adding these additional functions to your model, which kind of sit alongside your model's computational core, they're mostly descriptive. The framework can ask about your variables. It can ask what variables you have, first of all, what the names of them are. So that's over here. What are your input variable names? What are your output variable names? But then it can ask for each one of those. It can say, okay, you told me you have that model. What's the data type? What's the units? What's the item size? What grid is it on? All that stuff. So now it can ask all that stuff about those variables. It can also ask all about the time, how the time works in that model. It can ask about, it can control the model through these model control functions. So it says initialize, and it's like an orchestra conductor saying, go, and start, get ready for this next part. Update takes one time step forward, or you can update until a certain end time and finalize. And this is a bunch of functions not fully listed to describe your grid fully, so that if you have an unusual complex grid, it can pass that information to the regridder to regrid for you. And then you have getters and setters. So the framework can, once it knows you want to talk to another model, it can get your values, manipulate them, regrid them, unit convert them, and then pass them with the setter to the other model that wants them. And so it's a fairly simple idea. And these don't use object-oriented concepts by design. They're all, the arguments are all primitive variables, and returns are all primitive, even though some of these are object-oriented languages that we support. But that means that it's like dead simple for people compared to what it could have been. And that's part, I think, why we've seen the big adoption start to happen. Now, one of the cool things, and Tian Gan here at CSDMS has pursued this pretty far, is you can also use it with data sets. Like I said earlier, data set in a lot of ways just like a model with no inputs. And if you think about, especially about a gridded time varying data set, like a netcdf file that has a stack of grids, there's a time step between the grids. There's some type of grid that the values are on. There's variables, there's units. So it's all pretty much like a model, but you might not, in order to ingest that data, you might have trouble because it's not the same grid you use or the same units you use or whatever. But hey, we have mediators that take care of that stuff. So you can wrap a BMI around a data set, same as a model. And that's what's been done. But she took it even further, where a lot of these famous data sets had this done to them already. So if you use any of these other data sets, you can just use them as if they're a model and pull the stuff out of them without any work on your part. So that's very cool also. Now, one of the things I did, in fact, the very first thing I did when I started working with NOAA was they wanted to extend BMI because there were some things that couldn't do that they thought they were going to need to do, because they're going to run next gen on HPC systems and want to be able to load balance and run a model and then stop it, move it somewhere else and checkpoint it. So they had these additional objectives, and they said, well, what can we do about that? BMI doesn't do that. So I started looking into how to extend it in the minimal way possible and added some functions, turned about to 2, so that you could now deal with other variables besides your inputs and outputs. You could have other variables that are needed for serializing the state of the model, or even things like calibrating, because that's there certain parameters that you would use to calibrate or tune a model. And so this idea of variable roles came along. And this picture, what it depicts is a successful test where you have a model instance 1 and 2 of the same model, and you initialize both of them, but then you run this one for some number of time steps and stop it, serialize the state, save it to binary file, deserialize, put it in this one right after it's been initialized. Now it thinks in its mind, its brain, it thinks it's been running just as long as that one has, because it has all the same variable information. So then it updates N2 time steps, and that one does too. They both finalize, they compare the states, and everything's identical. So you could have moved that model to some other platform or whatever you want, and everything runs identically like it did. And the reason the little brains are here is this is kind of like if you've seen sci-fi shows where someone creates an android body and they want to copy the brain of somebody and put it in the brain of this android or whatever. That's kind of what we're doing. We're copying the brain, the life experiences of this model are being shared with this model, and it can just take up from where that one left off. Now, this is kind of a fun slide to have made. I was thinking about the BMI Council, which is this governance body we created to when BMI started to take off to try to get community governance. And it occurred to me it's a little bit like the Knights of the Round Table. So I started Googling for pictures of that. And this is something you can buy on Amazon. It's a 3D-dimensional object you can buy. And we have about 12 people. So this is almost the same number of people as around that table. And we're kind of like knights, we're like that. So anyway, we've been talking about all the people that came to this have different objectives or desires for what they'd like BMI to do going forward in the future. And one of them is parallel processing, which is something we never really supported before or in a minimal way. And so now we have experts on the team that are helping us to support that better. Then the model state serialization, which is something I worked on for calibration. So there'd be one calibration tool up in the framework. And if it knows what your parameters are for calibration, then it could automatically tune you. So you don't have to be calibrating your own model. You could use framework tools to do that. And that would be awesome because that's a hard thing. Also map projections and ellipsoids, which is something that our Mark Piper has worked on because we didn't really have that in the original BMI. So if you'd like to be involved, if you decide to become a fan of BMI and want to be on the council, just hit us up and we'll give you some work. So this next one is about the scientific variables ontology. And this one, I realized I had so many slides I really liked, I had a hard time cutting it down. So I'm going to try to go through it kind of fast. But, I do physical modeling and theoretical modeling. Most of the time, I don't deal with data problems, except in the last few years, I really got into that. And there's a problem that comes up, which is the semantic mediation problem, which I hinted at before, where all these models and data sets have their own internal names. They might call it streamflow, they might call it Q, they might call it discharge, but it's the same thing. But how do you know it's the same thing? And you can't couple them automatically if you don't know that this variable is the same as that one. And it can't be kind of the same. It has to be exactly the same. So like in heat capacity, there's 7 different types. You can't just say heat capacity. You have to say what type. And so all that has to be captured in metadata to allow this automatic coupling of models so it knows that this variable coming from here is compatible to that one that's needed over there. And so I got pulled into this much deeper down in the rabbit hole than I ever thought I would, thinking first that CF standard names would help us. And it kind of did help us, but it wasn't enough. And it wasn't as rules-based as this is. And so this started as CSDMS standard names, which I'll talk about in a second, but that's where it started. But then I hired someone named Maria Stoika a few years ago on one of my grants, and she helped to build it into an ontology, a formal ontology. So you may not know about these standards, but they're underneath all your web stuff you do. Whenever you shop online, there's these W3C standards that are underneath to describe the things you want to buy or the airline tickets or whatever. So RDF is a major web standard. Sparkle is used together with RDF, and there's the other ones in there. And so what we realized is we wanted to have a very robust hub and spoke solution so that all these different resources, models, and data sets could map their internal vocabulary to some central vocabulary and then back out again. And that's much more efficient than trying to map them pairwise all the way around the circle. They're mapping to an interior hub, but that means the hub has to be very expressive to be able to capture all the different concepts that might come up in these models. And so we started working on this, and we've taken it very, very far. And we've had multiple projects. CSDMS is where it started. I had 9 different EarthCube grants that I was funded on to work on some of this stuff. And Mint is a project with DARPA that we did. And so we took this much further than I'll be able to share today, but it's all there and it's online. Here's the basic problem that you have with semantic mediation is consider you have 2 hydrologic models. One has some output variables that are called stream flow and rain rate internally. That's just what they call them. And this one's got 2 models that it provide as input. So these are a natural pair, these 2 models, but it calls it discharge and precip rate. So how do you know that they are talking about the same thing with the same units or even the same concept? Because there's different ways to characterize precipitation rate. You can do it as a volume flux or a mass flux. It doesn't have to be one or the other. So that's something that could be a problem if you're trying to connect them and you don't know. In fact, a lot of the modeling problems they had in NextGen were because they were trying to couple 2 things, thinking it was the same concept, but it was a little bit different. One was integrating over a time step and one wasn't, or whatever. And so if you don't describe exactly what that variable is, you have problems. So this is some examples of how you might represent these names in the hub with very descriptive names with an object side and a quantity side and a double underscore to separate them. And we put enormous amount of thought into this, and it doesn't really matter exactly whether you like the way these look or whether you like the way they're called. The idea is that we have a general system for building them up for almost any scientific variable. And it's usually pretty clear to a scientist reading this what we're talking about. You may have to look up flux if they don't know that that's per unit area, per unit time, but that's what it is. So one way to think about this is when you write a paper, a scientific paper, a lot of times you'll include a list of symbols because you call it alpha, but nobody knows what you mean by alpha. So you say it's the diffusion coefficient of salt in concrete or whatever. You just say something that you think describes it to a human, but we're not describing this to a human. We're describing it to a machine. We can't just make it up as we go along. We have to have some kind of a system for building these things in a consistent way. So the next slide is another one of my favorites from a while ago, which is to just stop and realize that variables are super, super important to what we do. They underpin everything. This equation represents the relationship between variables. It's Navier-Stokes we use for a lot of our modeling. So they appear in our equations. We use their values and store them in data sets. We feed values of variables to our models and as inputs and outputs. And so if you can't handle variables, you can't really solve this interoperability problem. You have to have some way to deal with semantic mediation and be able to share variables because they're just super important. And there's been a lot of prior work on this kind of stuff that you can tap into. And you've probably almost certainly heard of the SI units, but you may not have heard of the sister, which is the International System of Quantities, which is ISO 80,000. And that's a whole different body of multiple books, lots of information. But it's based on this idea that you can introduce 7 fundamental base quantities, and virtually all other scientific quantities can be built up from those. And so these symbols here, these dimensions, are appearing in this equation with exponents. And if you want to represent something that's not here, like I don't see velocity here, well, velocity is length per time. So it'd be A is 1, and C is -1, and all the others are 0. Now I have velocity units. You can do pressure, you can do just about anything you can imagine in physics can be represented by some set of powers on these base symbols. So there's some order to our world of variables. It's not a bunch of chaos. It's actually got some deep structure and order to it that we can start to utilize. When we talk about these things as quantities, that's the term they use in ISO 80,000. It's a good term that we all kind of understand, which means you quantify something with a number in units. Now that's a quantitative property. There are also qualitative properties, which we got into for DARPA, which are things that can't be put in the system, but they're still of interest. Like for a person, you can measure the pupillary distance as a physical thing, a distance between their eye pupils, but you can't just measure their intelligence or their gullibility or their creditworthiness, but you'd like to, especially if you're a bank. So they've introduced ways to measure these other things. They're usually called scores or indexes or something like that, like the FICO score or the body mass index, which are designed to measure something they'd like to measure, like obesity, but there's no direct way to measure it. And so they introduce a kind of artificial way to measure it. And we had to get into that for DARPA, which goes outside of this basic physics approach. And I'm not going to talk about those here, but just know that we can handle that. Now, this is to kind of get at the idea that there's always two fundamental parts of a variable name to be unambiguous. You have to say what it is you're looking at or observing, and what quantity are you, or what property are you quantifying for that thing. And this picture was snapped on my phone from my house in Luquillo, Puerto Rico, just before Hurricane Maria hit my house. So I lost power briefly after this, but luckily I got this image first. Puerto Rico is 100 miles wide. This is like 500 miles across. This is a big thing. And the eye alone is like 30 miles. So this is a big hurricane, but that's as good a thing as any to think about. So let's think about hurricanes as something out there. Now, we have some terminology where a phenomenon is something like hurricane, but an event is a particular phenomenon occurring at a certain place in time. So Hurricane Maria is an instance of a phenomenon. It's instance of the hurricane concept. It's like classes and objects. And it has a lot of attributes if you think about it. Like, what's the diameter? I just told you it was about 30 some miles. What's the travel speed? They're usually kind of slow, something that linger. The direction at any given time, the maximum wind velocity, which is usually out here around this edge, around the eye. What's the air pressure? They have low air pressure in the center. So they pull a bulge of water underneath them. It usually comes and causes storm surge. The time it makes landfall, the category of the storm. So there's a whole, just for something like a hurricane, there's a whole bunch of variables that you might be interested in that you can write down. But these are the quantities, and this is the object. Now, as you dig more into this, there's state variables and there's process variables. Some of them are just describing the state of something. Like for a glacier, you have a mass and a volume, which is what it is. It might vary in time. But there's also these processes that the glacier is undergoing, like it's calving, melting, retreating, sliding, sublimating, infiltrating, whatever it's doing. And we might want to know how fast it's doing some of these things or how much it's producing when it does these things. And so if you take these process names and combine them with some kind of a quantity, you can start to quantify the process. So a process is something that's happening to an object. It's not the object itself, but it's this thing that's happening to it that you want to quantify and say something about. And this happens an awful lot in the sciences. And the process names, because they're getting at an action that happens to an object, they're almost always, or maybe always, obtained by nominalizing a verb, or converting it to a noun. So we know if we start with a verb and get all the verbs in the dictionary, which I've done, we can get all the process names known to man. Now, sometimes they're used in multiple contexts, like you can have migration, meaning bird migration or gene migration, or some other kind of migration. So you have to then disambiguate those. But the basic idea is these process names are verb forms. Now, the CSDMS standard names then was built on this idea of objects and quantities, but we also realized we need to add in operations, because sometimes you do a mathematical operation, like take the time derivative or take the x component of, and that creates a new quantity from the first quantity with different units. And so there's really three parts, possibly. And the way this left hand is constructed for the serialized form is it starts with the outermost concept, like atmosphere, to give you context. And it says something in the atmosphere. This is usually often containment. So carbon dioxide in the atmosphere has a partial pressure, and water in the atmosphere has a rainfall volume flux. And an ellipsoid model of the Earth has an equatorial radius, and so forth. And so that's the basic idea of how you do this. And if you're an author of a model or a data set, you make this mapping just once. You take your internal variable, maybe it's Q, and you map it to this thing somewhere, just like you do in a list of symbols for a paper, and it gets recorded. From then on, your users never have to do anything about this, because the framework knows this mapping, and all these other things did the same mapping, so it can disambiguate which things are compatible to connect and which ones aren't. And so it's pretty cool. If you're the author and you don't know what it is that you're dealing with, then you better figure it out, right? So again, we took this pretty far, and we used different symbols for different parts of this serialized form. So this one has double underscores is in the middle between the object and the rest of it. And the single underscore just separates words. A hyphen connects words that need to stay together, like carbon dioxide. Tilde lets adjectives trail. And this trailing is for a reason, because when you write these in a think of an index to a book. When you alphabetize these, you don't want the D to make all the seawater phosphorus stuff jumping all over the index, right? So you start with the thing you're thinking about, and then this specializes it to some particular situation with an adjective. And you can just chain as many adjectives as you want. And interestingly, all the operations, they tend to end in of. Whenever we talk about Laplacian of, function of, time derivative of, whatever, we always say of. So we just use that as the limiter for the operations. And so this is kind of the core of this. And just to remind everyone, you don't use these long names in your code because obviously they'd be a pain to drag around. You can call it Q, but you have to tell people Q means this in one mapping. And then that's it. You don't have to worry about it anymore. A really common pattern we came across as we started going down this rabbit hole was this idea of process name and quantities, which I hinted at with the glaciers. And it's kind of a cool thing to notice when you first notice it and you realize how widespread it is. It's a cool pattern because look at all these examples here where the first word is a process, the second word is some kind of a low level quantity. So if you're a martial artist, you might talk about the striking distance, your car turning radius, your car, in the back of your car's manual, it says the inflation pressure, but it's always a process on this side and something that quantifies the process on the other side. Gestation period, another one that's kind of interesting. Vibration frequency, another one. So it's a very, very common pattern. And there's usually just a handful of endings that will turn a noun or a verb into a noun. And they're summarized there. Similarly, operations are important, like I mentioned, because we often do something like a time derivative or something, some function, or an area integral or something. So this shows that some of the common operations and that they act on different types of fields and produce different types of resulting fields and how they change the units. If the units were initially U, then doing that operation adds up per time or an L squared or whatever. So they just, all operations do is they take an old quantity and make a new quantity. So they're on the right side with the quantities when you make the name. Another pattern that I think is cool because it shows the finiteness of this task. It's not as unlimited as you might first think. These red things here are all the things that you might conserve in a model, pretty much. I don't know, there might be something missing, but most models either are conserving charge, energy, mass, moles, momentum, number of something, like the number of people in this room, and volume. And so those are again, they're like your base conserved things, but any of them can be fluxing and flowing around from one place to another. And so then by looking at these endings that you can put with them with new units, you can quantify all kinds of other properties of how those things flux and flow around. And here's the field type, here's the modified units. And interestingly, if I said charge flux, if you know what flux is per unit air, per unit area per unit time, it's a charge flux. You probably know, even if you're not an electrical person, what that means because it's what charge is, what flux is. So that's per unit area per unit time. But that's not what they call it in electrodynamics. They call it electric current density, which is jargon. So we don't try to capture the actual jargon term, which we can do in our RDF stuff. We can capture synonyms if we want. We do. But in terms of somebody being able to map correctly, this is very almost self-explanatory. It's almost just defining itself. And that's how all these are. So jargon almost kind of leaves the picture here because you want people to just understand that they're mapping to the right thing. So that's enough about standard names for now. Unless you want to talk to me more about it sometime. But we took this really, really far. And Maria made a really nice website. If you go to scientificvariablesontology.org, she has a video on there you can watch. And turning this standard name stuff into an ontology was a big effort that she largely led that has, we're hoping it's going to take off in the way that BMI has. BMI uses standard names for its communication, by the way, to between the models. It's intended to be used that way. It's taking longer for people to realize the importance of that. So they like BMI, but they're not necessarily catching on to the standard name stuff. We're trying to promote that. And once they get enough objects, enough models and whatever, they'll realize that this is a lot better than trying to map them individually. So this is TopoFlow. I'll go back a slide. This is my a model I wrote over many years that's now in Python. It was in IDL originally. And this is one of the papers on it, more recent papers that talks about it and a couple of links. And it's a package, it's a Python package, but it's pretty elaborate because it took many years to write. So it's actually 98,000 lines of Python code. It's got a lot of stuff in there. A lot of different processes, utilities, regret, all kinds of stuff is in there. And it turned out that I already had TOPOFlow and IDL when we started trying to figure out this BMI stuff for CSDMS. So I used my TOPOFlow model as sort of a test case to see, okay, if we're going to break these models apart by process types, make components, and make them all communicate again to solve problems, how's that going to work? And how will it work? So TOPOFlow was like the guinea pig or test case for a lot of this early BMI development, and got completely torn apart and rewritten in Python as a bunch of BMI components as a way to figure this out. And turns out it's the first spatially distributed model ever to be used in next-gen, and I think the only one so far. And also the TOPOFlow repo was the first and maybe only open source model forked by NOAA OWP for their work. I'll talk about the TOPOFlow Glacier component that they built using some of the tools in TOPOFlow. I'm not going to go through this too carefully because I don't want to run out of time, but this is a picture from one of my papers that kind of talks about all the steps of setting up your model, where you download a DEM, and that sometimes maybe used to take mosaicing. Then you extract things like the flow directions and the total contributing area grid and other derived quantities from the DEM. Then you figure out where your basin outlets of interest are within that watershed. Then you parameterize things that you don't have a measurement for. Like we don't know the Manning's End everywhere in the river. We don't know the bed width everywhere. We don't know the angle of the banks. But we can parameterize them as a power law of area. And that tends to be pretty good because they tend to have a trend downstream as the basin gets larger and larger. So we can parameterize them with power laws and then download some meteorological data and some soil data, choose the components we want to use out of the set that's available. So one for infiltration, one for evaporation, one for snowmelt, configure each of them with additional settings, and then run the model and then visualize the output. So that's been the pattern of TOPOFlow for a long time. And this shows the different process components that are available currently to use with TOPOFlow. So there's 3 different ones for channel flow, some meteorological tools that include a shortwave calculator and a long wave calculator, evaporation by a couple different methods, including energy balance, which is the most advanced one. The glacier stuff that's been added recently, diversions like canals. Some of you may know that the Roberts Tunnel takes water from Dillon Reservoir and sends it under the Rockies into Denver. And so if you don't take into account that stuff, you don't get the right answers. And so it has canals and diversions, snowmelt by 2 different methods, and 4 different ways to do infiltration. And so you pick one of these or none from each category. You could just do rainfall runoff if you want to, and turn the other ones off, disable them. But you pick some, and then they get auto-connected by variable names. And because of that variable name stuff we talked about, they all use standard names. So you just pick them, and they realize that the framework realizes that all the variables that everyone in that group needs are provided by someone else in the group. As long as that's the case, it'll happily start the model. Otherwise, it'll say, I don't have a component that provides this, and it'll complain. But if they all match up, it'll just take off and run. So it's super easy to pair these up. And initially, Eric and I were thinking about having these components have a type, like saying that there's a type of component called an infiltration component. And we couldn't think what properties would fully define that because there's so many different ways to do infiltration. So then we thought it's better to just stick with variable names. So if you just say, these are the things I need infiltration rate, or I need this thing, this other model might need this or that, then they pair off just fine. And you don't have to actually define component types. So this is a quick example of something from one of my posters where it just shows running TOPOFlow inside of NextGen for a particular catchment called Cat 209, which happens to be in Maine in the Huck 1 area. And this was a particularly rainy event that's captured. And it's not even compared to observations in this particular plot, but it just shows you some reality there. And then this one is pretty cool because Lauren Balatin, who now works at Linker, she was working with me as a NOAA affiliate. And it was decided by our team, which was led by Keith Jennings, who's a snow hydrologist trained under Ann Nolan, um, that we needed some kind of a new way to do glacier melt in NextGen that was not what they were using in the National Water Model. National Water Model used Crocus. They had a lot of problems with it. And so they said, based on the expertise of these snow hydrologists, they said, we don't need all that. We just need this. And so they knew that I had some similar components in TopoFlow that could do snow melt. They said, let's adapt those because they already have BMI. And so they adapted them with the work of Lauren. And then this is an example of that she presented at AMS where she ran. So the top part is TopoFlow running for Wolverine Creek in Alaska, with the red curve being the observations and the blue one being the modeled. And the bottom one is the National Water Model version 3, where it's again red is observation and blue is what was there. Now the NSC and KGE metrics are somewhat similar, but this one's a heck of a lot noisier. This blue curve down here is coming from the National Water Model, and I don't know why it's jumping around so much, but that's not happening with the Tocopilla Glacier case. And so she showed in her talk that we could do pretty well with the Tocopilla Glacier as the new component. And there's only so many basins in the U.S. that have glaciers, but there's quite a few. And now that's the component that they're planning to use for those. And we're almost near the end here. We're getting close. So I mentioned NextGen in a box at the very beginning, which makes it a lot easier to use NextGen. And this was work by the Cairo community. And this particular thing was led by Arpita Patel. But they developed this Dockerized version of NextGen, and that turned out to be a huge help because NextGen is very complicated. It's got a lot of dependencies, supports all these different languages, Python, C, C++. So it's got a lot of moving parts underneath the hood. And that meant it was prone to failure if you didn't install it exactly right or if there was some kind of problem. So by Dockerizing it, it becomes really straightforward to use, and you can just put it together and use it. And they connected it with some nice visualization stuff developed by Dan Ames's group and others, like this tier stuff. So it's kind of an all-in-one way to run NextGen. And one of the last things I did before I ran out of money from NOAA was to add TopoFlow to that container. I've got a few details to work out, but you'll be able to run TopoFlow just as easily as you can run the rest of NextGen now in that box. Now, this is the last segment. I think I'm doing okay for time. Just a couple more slides. So this is called Harbor. This is an acronym I came up with because I was thinking of something that had RB in it that represented containment. And so I looked in the Scrabble dictionaries for short words that had RB that represent something, and I found Harbor. Well, then it turned out to work out great because it's harmonized attributes for river basins in one repo. And you'll see why that's a good name in a second. But this is the paper that's in the works right now, being submitted to Hess on this effort. And so the motivation is now that we have NextGen, we can run any model we want on any river basin we want in the whole US. Compare off however you think it's going to do a good job. But that means you have a huge combinatorial number of options for how you set this all up. So you'd like to know which model should I use with which basin. And part of it is just bringing together all these different river basin data sets, but also then looking at how do you tell if two are hydrologically similar? Like they're both from arid basins with other properties, or they're both from humid areas with deep soil or whatever. So what's a way to categorize them so you can know if they're in the same category, you'd expect the same model to do well for all the ones in the same category, hopefully, to sort through this complexity. And so I started working on this as a project where it ultimately ended up in 16,000 lines of code. But I went big. So I went to basically every river basin data set in the US from any agency, pull it all together in one place. That's why it's called Harbor. And so it has many individual TSV files. It has links to all those other data sets out there in one place. It's in a repo if you want to have a look at the repo. And there's some guidance there, but it was a big effort. And I'm not usually a data guy. I'm more of a theory guy, but I like things to be clean. So I took this on, and there were data sets like camels being used out there. A lot of machine learning stuff is using camels. That's 671 basins. There's MOPEX from many years ago, which was used for model calibration work. NOAA has all of its RFC basins. USDA has its experimental watershed network. USGS has Gauges 2, which is a really super great resource. Um, there's many more. I found all the CZO basins, all the LTER basins, any kind of basins I could think of that I've heard in any hydrology talk in my life. I tried to pull them all into one place and clean them up and make them accessible. And uh, and so the attributes that are now a lot of them had their own shape files or whatever, and those are accessible in this collection. Instead of going and digging for them, you just go to this collection and just find them right away. But in addition to that is a big spreadsheet with about 30,000 basins in it, which has all these 51 attributes for each one, like which data sets is it a member of out of these? Because there's a lot of overlap in these. Or what's the bounding box so I can get it from NextGen to model the watershed and download a DM for it. Or lots and lots of other things. Units of elevation and contributing area, ecological region, the seasonal water balance classification. These are 4 different ways to classify the basins on hydrologic similarity. And then I found it looks kind of like this. That this is not to scale, but these are some of those data sets, and there's a lot of overlap. Like Mopac's in the middle here and overlaps almost all of them. Camels is fully contained in the Gauges 2 select basins, which is contained in the Gauges 2 reference basins. And then there's non-reference basins separately, and there's all these NOAA RFC basins which overlap with some of those, and the federal priority stream gauges system. And so there's all these systems, but they're all sometimes they're tapping the same watershed with the same ID. They just happen to be included in multiple places. And you want to know that. If something like, you might want to choose a watershed that's been part of several different studies. So if you go the ones right in here, you get a basin that's been studied by everybody and maybe have a lot of data with it. Now, this figure helps to make you understand why it's called harbor. So these container ships are meant to represent federal agencies. This is the USGS ship, and this is the NOAA ship, and this is the EPA ship or whatever. And these containers are all their little data holdings. And these cranes are the Python code that I'm using to pull their stuff out and put it on shore. So that's kind of the metaphor for this. And and if you go to that website, you can see more what it's all about. And I think this is my last slide, which is one of the methods that was highlighted in this work was something called the seasonal water balance method by Berghaus et al. 2014. And it's a process-based way to try to define a limited number of groups of hydrologically similar basins. So it has 10, which is a nice manageable number, 10 types of basins categorized with things like whether their precipitation and evaporation are out of phase or not, whether they have any snow domination, whether they're ET and precip are in phase, and seasonality. So this work they did is based on a lot of prior work that realized these are kind of the fundamental things you need to think about. And it was a pretty clean system, except it turned out that if you used it directly out of their paper, about half the basins didn't get classified at all because there were gaps in their classification. So one of the things I did was to close those gaps. So now that same system classifies any basin you want. There's no gaps anymore. And so then this is all the Gauges 2 reference basins in the entire United States classified by that system. And this full classification of all of them is not in the the version that you'll find on my GitHub doesn't have all this yet. That's about to be pushed up to there soon, but it's done. It's been finished. If you do work with river basins and want good data, the Gauges 2 effort that came out of USGS is really amazing. It's got lots of spreadsheets and data beyond your wildest dreams almost for over 9,000 basins, about 2,000 some reference basins that are considered more pristine or less human influence, and then about 7,000 others that are the non-reference basins. And so it's just a really great resource that should be more widely appreciated. And that's it. And I wouldn't follow these QRC codes if I were you, because these are from an old talk, so I don't know where they're going to go.
Hey Scott,
Yeah, Albert.
thank you for your talk. Um, What happens if one of those databases gets a, new version, another 100 USGS is adding another 100 stream gauges, and this
Someone would
might
have to
not
do
be
something to
realistic, but
deal with that, but more likely they're going to take away gauges than add new ones as they keep doing that. But yeah, not everything that those data sets have is captured here. This is more of a data sheet with pointers to all of it. So if you were to go and try to find it all yourself and Google around for days and days just to find it and how to then read their instructions, how to download it and whatever, I have these little readmes that describe that full process for all these different data sets and then links to where the actual data lives. So I'm pointing, I'm not just having my own stuff, but I'm pointing to where you can find the source of the data and the shape files and whatever. So it's like just a huge like sweeping across this literature and trying to pull it all together in some standard way. Anybody else?
Thanks for the talk. Um, I was curious in like the last few years, there's been a lot of advances in AI.
Mhm.
And so I was curious how this sort of playing into what you're doing and some of the changes that have come about or not come about or
Yeah, I've started to play with AI a little bit, and I think the complexity of something like this, I don't think they're there yet because it's so messy. One of the problems you find is you'll find a NOAA RFC spreadsheet or something that has data in it, but it'll have a lot of missing data. It has huge amounts of things that someone just didn't fill in. They didn't feel they wanted to or whatever. But it turns out there's 4 or 5 different of these out there. So I was able to actually collate and fill holes by comparing all the ones that I could find across the internet. So it's just a huge amount of Googling. And then once I found it, I'd find that the format was weird. So I'd write a Python script to like pull it out or clean it up or fix something or whatever. But this stuff is scattered all over the place. There's some of it's like the CZO stuff is in the HydroShare. That's the only place you'll find the CZO basin data, except for now in Harbor. But so yeah, someday maybe AI will do all this house cleaning for us and make it easy. But I don't think from what I've seen so far, even in the coding examples, it's not doing very well with coding. Like a lot of times I don't go seeking it, but I see it in the top of the Google searches, and a lot of times it's just wrong, and I just know it's wrong. Or it'll show me some code snippets, and I'll think, well, that's great. I'll try to use it, and it doesn't work. So they're not there yet. Hopefully, maybe someday.
This was a great talk. I was just going to ask, I guess, a follow-up on AI. Like, I know that there are natural language processing models that sort of can take, human speech and like have a machine interpret it kind of. Is that sort of when you were talking about AI is not quite there yet? Were you also referring to NLPs or like, I guess, could NLPs potentially be a direction to more generalize and like expand the scientific variable
Yeah.
thing?
Yeah, no, I was thinking more about Harbor, but you're right. Maria has actually tried some of the AI stuff on, like, you take a paragraph that describes a variable or something, and then she'll use modern methods to try to match it to one of our terms, and then it'll rank the matches to see which one comes the closest. And it might say this is a 70% match and this is a 20% match. So there are things like that to do, but and AI can be helpful that way. And I've actually been giving invited talks at AI conferences because of this stuff that it really is natural language stuff. But there are I hope what came across is there are rules. There's a structure to this. It's not like when I first thought of it, I thought, man, we use all these different jargons and it's probably like a nightmare to try to sort it out. But it turns out there's a lot of structure, like deep structure that can unify and pull this together. And ontologies capture that structure. And machines can use that ontology. In fact, a lot of what's happening on the web is using somebody's ontology that they already have to make it all work. And ours is now one of those in that mix. But yeah, there's but a lot of things have flaws. Like Sweet is a ontology, a system that's been out for a long time. It's an acronym. Can't even remember what it stands for. But it turns out that the best it does is says that heat capacity is something. But there's 7 different types. I took a thermodynamics class. And there's capital C sub P, little c sub P, capital C sub T, little c sub, there's all these sub concepts. And if you don't know which one it is, your models are not going to work right. So we really went down like disambiguating these things. I learned that there's like 7 different types of latitude. I thought there's just one, but there's like 7. So we went really, really, really far in this direction and learned a lot of stuff. Another cool thing is that quantity names are often adjectives that have been nominalized. And there's a few of them that are very familiar to us that all end in th, like width from wide, and depth from deep, and height, and girth, and birth, and wealth. And it's just a handful, and they come from Old English. And that they're so fundamental. You want to know how wealthy someone is, or how wide the boat is, or what, so they're very fundamental quantities, but they're the only ones that have that ending. And so I learned all kinds of natural language stuff. So I was doing this. All right. Thank you.
Slide published the harbor
Not yet. No. Oh, it's about to be, but it's not quite there yet.
okay, because it's kind of cool. It's a neat